Okay, great, you're back. Here it is. We're on the fourth part of this Module 3. We're going to be continuing to work on how we're going to make Project 1 work, where we are going to be modeling the amount of solar radiation incident upon a solar panel. We're going to start kind of putting these ideas that we've seen in the first 3 lectures together. How are we going to actually model the flux of solar radiation at this panel? And let's think about it this way. How are we going to determine the amount of power that's available to this particular solar panel? Like, I got a little panel here sitting on the roof. How do I decide? Well, first of all, we're going to have to figure out a way that we're going to describe how that solar panel is positioned. Now, different sources I looked at had different ideas as to how to describe how a solar panel is positioned. And we're going to be using the notation here that we're going to be describing the panel's orientation at the site in terms of a vector normal to the plane of the panel. So here is a panel sitting there at some particular angle on the roof, and if I thought about it as like there's a vector that is perpendicular, that is normal, to use the right word, to the plane of that vector, to that solar panel, that's how we're going to describe the orientation for our purposes. So I'm particularly happy with how that slide worked out, by the way. I like the shadow that comes off the arrow. Anyway, we can describe then the orientation of this panel in terms of an azimuth and an elevation, which I'm going to just write as phi panel and psi panel. So these are going to be describing the elevation angle and the azimuth angle of a vector normal to the plane of the panel. Now, for fixed panels that are going to be, which is how we're going to be doing Project 1, we're going to be assuming, I think we can make a reasonable assumption that we're always going to want the panels to be facing south. Our azimuth will always be 180 degrees or pi, depending on whether you're using radians or degrees. The question is, what is the elevation angle of this going to be for the panel here? I mean, if you had a sun tracking solar panel where there is software actually keeping the panel pointing in the same direction as the sun, well then the azimuth and the elevation angle of the panel will continuously change, but as long as it's set up right, the good news is the panel is always oriented to be perpendicular, normal to the rays of the sun, and the collection of power from the panels will be will be somewhat greater. So for a sun tracking panel, the angular separation between where the sun is and a vector pointing normal to the panel is going to always be 0. There's going to be some direction in the sky, some combination of elevation and azimuth where you are looking that is where the sun is, and then there will always be some orientation of the panel, some vector that is normal to the surface of the panel. There'll be some separation between those two, except in the case of these sun tracking panels. For these sun tracking panels, then you'll want the angular separation always to be 0. So, here's our fixed panel. We aren't in general going to have the sun exactly in the same direction as the orientation of the panel. In general, the sun will be pointing us different direction, and so there'll be a vector that describes the direction where the sun is right now, the azimuth and elevation of the sun, and there'll be some elevation and azimuth that describes the orientation of the panel. And the question is, how different are they? That's what's describing how much radiation is incident upon your panel. Now, I didn't find any consensus as to what symbol to use for this angular separation between the two. So we're going to just pick a symbol. We're going to use lowercase zeta. Okay, lowercase zeta is going to be our symbol for the angle between these two, between two locations in the sky. One being the direction the panel is facing, and one being the direction of the sun. And oh my, look at that, a whole mess of trig again. Lots and lots of trig type functions or whatever, but notice what it depends on. I mean, there's going to be the properties of the panel itself, the elevation angle of the panel, the azimuth angle of the panel, those are going to be in there. And notice that there are going to be properties of the position of the sun in the sky. Places like the elevation angle psi and the azimuth of the sun, phi s. These are properties of the position of the sun, which themselves are, looking back on previous lectures, these also themselves then depend on things like the latitude and the longitude of your panel, the time of day, the day of the year, all that good stuff. I mean, this equation is awful, and it has tons of awful things inside of it. I mean, when you think about those giant equations that we've seen so far, they're in there. They're hidden. I mean, where we have a psi right now, well, that's actually tons of math just to get to that psi. But basically, once we're ready to do this here, there's going to be 3 basic steps at any given time to find the instantaneous solar flux. This is not the answer to the question in Project 1, but it's going to be part of how you get there. So there's going to be basically three main factors that are going to be determining what is the flux of solar radiation on your panel. Basically, one is we're going to have to determine how much radiation is getting to the top of the atmosphere from the sun. Now, this is going to be related to the Earth-Sun distance and that inverse square law and so on. To help you along the way there, I kind of simplify it. Rather than make it so many equations, I kind of did some of the math here for you, and we have now this expression here where S is a function of T. S is going to be the solar flux at the top of the Earth's atmosphere as a function of the day of the year, what time we're at, you know, the T being like the Julian day of the year. And then there's all this stuff on the right-hand side. It's going to depend on our accepted value of the solar constant. We'll use 1,368 watts per square meter for that. That'll be just fine. We will have the Julian day. We'll have the Julian day of January 3rd. And we'll have the length of the year, 365.25. So by simplifying the math here a little bit and making a few assumptions, I kind of got you a step of the way along the way here. This is telling you then, I mean, if you made a graph of this equation, for example, and I kind of recommend you do, you'll see that, yes, there are times of the year where we get a little more than 1,368, times we get a little bit less than 1,368. Okay, then the second part is we have to also figure out how much radiation is actually making it through the Earth's atmosphere. The Earth's atmosphere is not transparent to solar radiation, although it is mostly transparent to solar radiation. But some solar radiation is actually absorbed by air molecules, especially ozone. Some solar radiation is reflected by aerosols in the atmosphere, things like that. We're not worrying about clouds. Clouds would add another whole level of complexity to this problem here. So we're just taking a look here at how much radiation is making it through the atmosphere, and I'll use the symbol T atmos to be the transmissivity of the Earth's atmosphere. Transmissivity of the Earth's atmosphere is going to be a number between 0 and 1 that says what fraction of the radiation that comes in at the top of the Earth's atmosphere makes it all the way down to the surface, past all these absorbing bodies like ozone molecules and aerosols and so on along the way. So if we multiply our flux of radiation at the top of the Earth's atmosphere by the transmissivity of the atmosphere, you get the amount of radiation down at the bottom. It's worth taking a moment here just to mention what is all this stuff on the right-hand side. I mean, I have great confidence that you can code that up in Octave, but what is this stuff? That 0.15 is a number called the optical depth of the atmosphere for shortwave radiation. Atmospheric science students will know what that is. It's a measure that is describing basically how effective the Earth's atmosphere is at absorbing radiation along a path as the radiation goes through the Earth's atmosphere. Now, this happens to be the value for all visible wavelengths, which is in general what solar panels collect and convert into electricity. So that is a fact. Now that particular term though, that value, 0.15, is actually the optical depth of the atmosphere on a straight path from directly above you through the Earth's atmosphere down to your location. In general though, the sun is not directly above you. In general, the sun is at a different angle. And some elevation angle. See how there's a psi in there? So, if you go straight, if the sun were directly overhead and the sun's rays were shining directly through the atmosphere down to your location, that's in many ways, that's the shortest possible path through the Earth's atmosphere. If the sun's radiation is coming from a different angle, it's passing through a longer path through the Earth's atmosphere before it gets to your solar panel or your surface or whatever. So we have to actually take into account the elevation angle of the sun because that changes the geometry. It makes it take a longer path through the atmosphere than if the sun is directly overhead. Mathematically, if you work through the trig there, you find out that path by multiplying the optical depth of the atmosphere by 1 over the cosine of that number that's given there, pi over 2 to minus psi. Again, it would take a bunch of trig to prove that, and this is not a trig class, we're just using trig. So I just wanted it not to be a mystery there. Those terms there are about how effective the atmosphere is at absorbing this radiation and the geometry of how long is the path through the Earth's atmosphere so that you can come up with an idea of how much radiation is making it through the Earth's atmosphere. Okay. And finally, we need to find out how much the beam spreading is happening when the remaining solar radiation that did make it from the sun to the top of the atmosphere and then through all the atmosphere down to the panel. We need to know the geometry of how those rays are coming in compared to the orientation of the panel. That's that zeta stuff, the angular separation between the rays of the sun and the orientation of the panel. And amazingly, that just works out to cosine of zeta. Now, zeta itself is horrible, and zeta has all kinds of things in it, like elevation angle themselves were horrible, but that doesn't look so bad. Okay, so it's just the, which by the way, you can see now why a sun tracking panel would work. For a sun tracking panel, zeta is always 0, so the cosine of 0 is 1, so we're multiplying by 1 all the time. So this actually, you can kind of see what's going on here. So, therefore, the flux of radiation at any given time on our solar panel is, gosh, that doesn't look so bad at all, S T atmos cosine zeta. Okay, it's going to give us a flux of radiation, so it's going to have units of watts per square meter or joules per second per square meter or something like that. Now, each of those terms has all kinds of horrible things in it, but fundamentally that equation there in that little red box, that kind of is the model. That is basically what you're trying to code up. You just got to make all those terms work. This is the flux of solar radiation on our panel. Alright, so this is what we're trying to compute, but it is instantaneous. That is the flux on our panel right this second. Now, in order to make this the total amount of energy over the course of, say, a day, we need to integrate this value with respect to time. We need to integrate this equation, this from sunrise to sunset. Now, of course, we are not going to really be integrating. I mean, integrating something that had st times cosine zeta doesn't look so horrible until you remember what's inside of that s, what's inside of that t atmos, and what is inside of that cosine zeta. Oh my word. Integrating this would be impossible. But we're not really going to be integrating it. We're going to be doing the kinds of tricks that we learned back in the second module, like trapezoid rule integration. We're going to gladly let Octave come up with a numerical approximation to the integral. It'll be close enough. So let's see here. That's fundamentally what you do in this project. You are going to be computing you're going to get your project working so that it can compute the flux of radiation from the sun on your panel at any given time, and then you're going to compute it for all the times of the day from sunrise to sunset, and then integrate that up to find out what is the total amount of energy per square meter that the solar panel was able to collect. Pretty slick, right? That's pretty much just what your project is going to be. Now, in the next video, we're going to be starting to walk it through how are you going to actually do that. I mean, I realize this has kind of been a bit abstract so far. But before we get to that point, let's actually answer a quick couple questions about how this is all going to work. I said here, in this class we are expressing the orientation of the solar panel in terms of A, the angle it makes with respect to the ground, B, the elevation in an azimuth angle of a vector normal to the panel, or C, the orientation of the panel with respect to the prime meridian. I hope that question isn't too hard. But anyway, you make your choice from the three options below, and I'll give you some feedback and we'll move on to question 9.